Hey guys, welcome to another video. Here we're doing contrastive learning and we're going to use a Sarcasm dataset. Contrastive learning is a very nice technique to actually properly fine-tune our embeddings, and we will see the performance very soon. So what is contrastive learning? It's simply just a learning technique that pushes symmetrically similar embeddings closer and symmetrically different further apart. So that's the very simple intuition. So we can actually use triplet based contrastive loss, and it basically works in this principle. Suppose you have an input which acts as the anchor. For the anchor, we have to pick a negative and positive sample. Positive meaning symmetrically more similar and negative being symmetrically more different. And the way we pick this is actually very dependent on sampling techniques, and you will see the effect of it later. So here, we have this loss function, which is just simply the max of the distance for the positive minus the distance to negative plus a certain margin. So when you look at the diagram, it basically attempts to push positive samples closer and negative samples further apart. So suppose you have a input example like Raytheon means humanitarian award, which is obviously very sarcastic because Raytheon is a defense company. Suppose we have a positive sample, Doctors Without Borders receive global humanitarian award, which is not sarcastic, it's a fact. They are an ethical group, right, after all. And we have this Monsanto named environmental hero of the year. And if you know, Monsanto has actually many controversies regarding environmental stuff, so obviously it's very sarcastic. So you want to push the anchor and the Monsanto named Environmental Hero of the Year more closer, and the Doctors Without Borders further apart. So here it's just simply pushing same labeled sarcastic ones closer together and opposite label samples further apart. So how can we actually visualize our fine tuning? So we know we got embeddings very high dimension. So BERT outputs dimension up to 768. So we can use this technique known as t-SNE, which is stochastic neighborhood embedding, which is just a dimensionality reduction technique that transforms high dimensionality data to 2D and 3-dimensional. How it does that, it actually uses KL divergence to reduce the difference between the two probability distributions between 2D and the high 768 dimension. So all it does is that it ensures that points close in original space will also be close in the reduced dimensions, preserving local neighborhoods and helping us visualize. So as you can see, on the left side is before we actually fine tune, the embeddings are very mixed together. We can't actually differentiate it in the embedding space. But after we actually fine tune, it's very nice, and the purple is on the left and the red is on the right. And this actually shows that the model, after fine tuning, is actually able to distinguish sarcastic and non-sarcastic in the embedding space much better. And correspondingly actually get higher performance that we will see later using simple logistic regression. Okay, so how do we actually pick our positive and negative sample? So intuitively, we do not want to make this too simple for a model. So if we have a positive sample that we have to pick for anchor, meaning that we have to pick a same label, we want to pick the least symmetrically similar sample and vice versa for negative. So let's take an example. Wow, what a fantastic meeting, I only lost 3 hours of my life. So this is a sarcastic sentence, and when we want to pick our negative sample, that means we want to pick a non-sarcastic version. We should not pick an easy sample like I had a productive meeting today. We should instead pick a more harder sample like wow, that was a fantastic meeting, very informative and engaging. Yes, both easy sample and hard sample are not sarcastic, but the hard sample here actually seems much harder. It actually seems more ambiguous, so some people might actually think that this is sarcastic. So we should pick a harder sample so that our model can actually learn better during our training. And this technique is known as hard sampling. So other techniques includes random sampling, semi-hard sampling, and distance weighted sampling. But what do you actually consider similar? So we keep using the word semantically similar. And it can actually be from a lot of metrics such as using simple Euclidean distance, cosine similarity, or over more complex ways like using sentence transformer embeddings. Sentence transformer is just another model actually built on BERT, and its just main purpose is to output sentence embeddings. And you can actually use TF-IDF, which we will later see is actually not so good. So sampling technique actually matters. So we select our positive and negative samples relative to each anchor, and the strategy that we do so actually significantly impacts the learned representation. So earlier we talked about the similarity metric that we're going to use, and suppose we use TF-IDF to do our hard mining to pick our best positive and negative sample. So what is TF-IDF? It's basically like a bag of words technique that represent the frequency of words in the corpus, and it only captures very surface level semantic meaning, and the effect shows. So when we use TF-IDF to actually do our hard mining, we can see that the clusters go from mixed to slightly less mixed. The samples are just not as good when we compare it to the previous one over here when we use random sampling. So our sampling technique actually matters, and we should explore it as well. So now we actually proceed on to the full code. So first things first, we're going to get our train indices and test indices, and we're going to use df.index. We don't want test site, and we're actually going to go ahead and use stratify to ensure there's a fair distribution of targets in both the train data frame and the test in data frame. So let's just use stratify. Df is sarcastic, and we don't really want to use test size. We're just going to leave it to default for now. So I should get our train indices, and let's get our train data frame, and we're going to get our test data frame as well. So we're going to use df log train indices and df test similarly, and just in case, we're going to go ahead and reset the index to ensure that the row indexes are reset for both. Okay, get our data frames. Okay, so now we're actually going to get our targets of our train and test. So simply take from our data frame itself is sarcastic, get the values. Similarly for tests. Okay, so now we can actually get straight right into the model itself. So let's just some text just to make it clear for us in the future. So first things first, we have to understand how BERT actually works. It isn't just like a LSTM model in Torch where we just put in the input right away. We actually have to use a tokenizer from BERT, which tokenizer will then give us the input that we can actually pass into BERT. So use a tokenizer of auto tokenizer and get the model similarly using BERT based uncased. There are actually many other models you can use, but for the sake of this tutorial, we're just going to use BERT based uncased. Okay, and since we're using T4 GPU, we're actually going to leverage our GPU by using the device and using the CUDA if it's available, and put the model to the device. So we're actually going to load the model first. Now, meanwhile, while the model loads, let's actually go ahead and try to understand how BERT actually works for those who are not so familiar. So, suppose we have text like I love NLP. What the tokenizer would do is take in the text, make sure it's on device so there's no mismatch, and let's actually view what the tokenizer outputs. It basically gives us this dictionary which contains three important things of input IDs, token type IDs, and attention mask. What you can actually do with this input is to pass it directly by using this double star unpack operator, because model expects input IDs, token type IDs, and the attention mask. So let's actually go ahead and print that out, and you should notice that it outputs last hidden state tensor and a pooled output tensor. Now for the sake of this tutorial, we're just going to use last hidden state, and last hidden state is basically going to be the output of all the different tokens in the last layer itself. So let's actually get the that value, and we notice this tensor. So once we actually view the shape, it will be more clear. So we get this 16768. So what this means is going to get batch, sequence length, and hidden size. So why is it 6 and not 3? Because of the way it tokenizes it. It's not going to be just I love love is going to be one token, maybe it's split up, and NLP is going to be split up based on its own rules of tokenization that happens. So it's going to be 6, and 768 is going to be the most important value that you have to remember. Is going to be a size of embeddings that we're going to work with. So this 768 is for each of these tokens, but we're more interested in the first token. So how do we actually extract it, and we're going to use colon to get all the different sentences in the batch, get only the first token, and get all of the elements in the 768, because we want the full 768 embedding for the first token. So let's print that out, and you get 1768. So this represents the embedding for the first token, also known as the CLS token. By convention, it's going to be the sentence embedding. You could use the pooled output, and that's actually fine as well. But by research, mostly use lossand instead because there's less abstraction. I mean, there's less. Um, they have more control in a sense because you're using the raw here embedding. Okay, so now that we actually have that, we are going to get the BERT embeddings. So let's just. We actually want to view the visualization for the test embeddings before we actually fine tune, just to get a good idea of what it looks like, and actually helps us to appreciate what our contrastive learning does. So we actually want to get our test embeddings first, and it's not as simple as just passing in the tokenizer and then just put in the entire data frame here, which would be nice to do, but when you do this, it actually will result in an exception because it uses too much memory. And so what we actually have to do is actually process this df clean headline in actual batches, and that will actually allow us to get our embeddings. So let's just create a function that we can keep reusing. So def get CLS embeddings, which takes in text, model, tokenizer, max length, and batch size. So let's just define some default values. Okay, let's initialize our embeddings array. Ensure the model is in evaluation mode. We don't want to do any backpropagation, so use touch no grad as well. Now we want to process it in batches, so let's just initialize our for loop such 0. We're going to get a number of samples first. And then batch size. So this is your start, your end, and the increments, the step increment. So we're going to get our batch texts and use slicing to get our text. Okay, but when I try this and I just use batch text, actually I get sometimes I get an error that some of it is actually not a string. So we want to actually go ahead and make sure every single element in the batch text is a string. So let's just use comprehension here. So just make sure that every instance of the batch is a string, and if it's a empty string, like just the length is 0, just replace it. And if it's not, just use a convention, just use a padding replacement to replace all the non-string elements and those empty strings as well. Okay, and if it's actually empty even after all that, then simply just continue. We don't want to tokenize an empty batch of strings. Okay, so we actually go back to what we are familiar with and actually pass in the batch text into our tokenizer and use these inputs to pass into our model. Okay. Another thing that we can actually do is actually pass in the inputs and ensure it's on device. So the code has been suggested here. So remember, K is your key. So if your input IDs, your token type IDs, and attention mask, and ensure that all the different tensors, for example here, this tensor will be on this device, this tensor of token type IDs will be on this device, and the attention mask tensor will be on this device. So by doing so, we actually can leverage our GPU and make sure it's A is consistent and B is faster. Okay. And another thing that we want to note is put padding instead of true, just put it as max length. This prevents any errors in the future where you get inconsistent tensor length exceptions. Okay, so once you get our inputs, you pass in the inputs, use a star operator, get the last hidden state as we went through here, and extract out the first token. And then once you get the outputs, pass in, make sure it's in CPU, and then get the numpy representation, and you can just append it to our embeddings. And once we do so, we can just get the numpy array of the embeddings in numpy form. Okay, so let's go ahead and get our test CLS, and I'm going to get our train as well correspondingly. instead of using values, we just use toList, for example. So we're just going to get the list representation. There's many ways of doing this, so it doesn't really matter. And you can get same as that. Okay, and let's go ahead and run it. So just for a fix, instead of using append, please use please use extend instead, because append will append the entire list itself, and then we have to use numpy concatenate on top of it. So you just skip all that by using extend and just add all of the elements, and then you're able to run this without any issues. So let's go ahead and actually use our stochastic neighborhood embedding to actually visualize our test embeddings and to get a representation in 2D dimension. So we have this plot embedding, which I'm not going to go through, it's a bit too long, but the idea is that we pass in the 2D embeddings inside, pass in the labels, whether it's non-sarcastic or sarcastic, and then we'll be able to visualize it. Okay, so first things first, we want to get our 2D embeddings using our test embeddings. So first things first, we have to go ahead and import our t-SNE package. Okay, and then we're going to get a sample of 1000 random test samples, so we don't actually waste a lot of computation power just to get all the test ones. So 1000 is enough to get an idea. Okay. And then we're actually going to get our 2D embeddings. So we're going to use t-SNE n components equals 2, so because it's 2D, random state 42, perplexity, and iteration, which is going to put about 300. I'm not spend too long on this. 300 is enough to get an idea anyways. And then we're actually going to fit transform onto a test CLS and make sure that they actually use sample indices. Okay, and let's actually go ahead and run it. And while we're doing so, make sure we go ahead and get our labels as well. And then we can actually go ahead and plot our embeddings inside. Oh, sorry, make sure to run that first. And as you can see, the visualization works, and your purple is your non-sarcastic and your orange is sarcastic. And as expected, before we actually fine-tune itself, the embeddings are all over the place. They don't really form any clusters, they don't have any separation between sarcasm and non-sarcasm. So this is the stepping stone that we can actually start to work on and get a better model. So let's actually get into our training itself and form our data sets and our models, and I'll be right back. Okay, so let's actually go ahead and form our data set. Call this section data set. And for our sarcasm data set, what we're going to work for here is just going to get random sampling. So random sampling is to just pick any, for example, for a negative sample, we're just going to pick any negative sample for anchor and any positive sample for anchor. And by doing so, we don't really have to go through into the sampling techniques because that's not the scope for the first tutorial, but we're just going to get an appreciation of picking positive and negative samples for anchor. So let's actually go ahead and create this. So self text labels, tokenizer, and your max lengths onto it. Put in our tokenizer as well, and your max lengths. Okay, now the next important thing that we have to do is actually store the indices of the positive and negative. The reason for this is because, well, once we have for anchor, if the anchor is a sarcastic sample, then we want to know the indices of all of the non-sarcastic samples and the positive samples, so we can actually get our actual text for positive and negative. So let's go ahead and initialize a dictionary to store all that. And I'm just going to use a simple for loop to do this, to store the indices inside. So if labels are not in self label to indices, and then we're actually going to put typing be done faster by collab. Okay, and then we're gonna finish up with the length function, and the most important one is going to be our get item. So get item is where we're going to actually define our actual dataset item is going to be retrieved when we call the training inside the inputs and outputs. So text label and label text and label is going to be our anchor. So let's just make it clear with anchor text and anchor label. Okay. Now we want to work on the opposite array or opposite label first. So remember, we want to pick any random opposite label. We also want to pick any random same label but with different index, because obviously the same label could contain the same anchor text itself. Maybe we don't want to pick the same text, then we won't be learning much. So that's something we have to mind. So let's go ahead and get the indexes for the opposite index. So get self label to indices and 1 minus label. Since we know this is a binary classification, it's either sarcastic or not, we'll go ahead and just use 1 minus label. Then use opposite index and just get a random one, and use this opposite index to get our opposite text simply. Okay. Now we do the same. Let's just get that. But instead of doing just this, instead of just doing this, because it could contain the same one, we want to ensure that it does not contain the same index inside. So and now the addition is going to be if I not equals to index, and the rest remains the same. Simple as that. We managed to get the opposite text and same text, and now we can actually go back to what we know, use a tokenizer to actually get the anchor inputs, the opposite inputs, and the same inputs. Same meaning positive, but yeah. Ensure your padding is actually max length. You don't get any inconsistent error later on. So right now, oops, sure that's okay. Yeah. And then we should go ahead and return a dictionary of all these values. So anchor k, and okay, the thing is, we're just going to return the batch size instead, and we don't want the batch size, so we're going to squeeze out the first element. Okay, and we don't need that, because all for triplet loss we just need our opposite and same, and that's how it's going to work. If you're familiar, if you see it as positive and negative, then just ensure that it's positive inputs and negative inputs, so whatever to make it clear. So, or if it's clear to you that you can see in a light that's opposite and same, then you just name it as such. But the idea is this is going to be a negative, this is going to be a positive sample. Okay, so that's going to be our dataset. So let's actually go ahead and get our train dataset. And we're going to get our train data loader. Just ensure this is anchor label and not label, and just rerun it and get our new data loader. Okay, so we're actually going to go ahead and actually create our wrapper model. And we don't want to use fully connected layer because we're not doing our actual classification itself. We just want to output the embedding right away. The reason why we have a wrapper model is because we want to create projection hits or some other layers that you wish to augment your embeddings, then you may do it here. Okay, so in your forward layer, we're going to pass in input IDs, tension mask, token type IDs, which is what your BERT essentially expects as well. Remember when we use the double star operator to unpack all of it. So return self.BERT and pass in all of these input IDs, attention mask, token type IDs. But remember, we want the actual embedding itself, so go ahead and use the last hidden state and the first token of the last hidden state, and you get our contrastive BERT. Okay, so let's go ahead and actually create our model. We're gonna create a new model from a fresh one, pre-train and contrastive BERT, and we're gonna put it to device. We're just doing a single line here. Okay, great. So we're gonna initialize our triplet margin loss function, and this is from PyTorch's loss function, so it's going to create our own one, which is great. So all it does is take a anchor, positive and negative, and train so that I'll create optimizer as well. So this is just common PyTorch stuff, so nothing new. We show the differences in the training as well. Okay, go ahead and load that. So let's actually get into our train function to actually fine-tune our BERT model. So it's very similar to other PyTorch code as well. Only difference is, for the batch that we retrieve, instead of passing the batch right away, remember in our dataset we have anchor and opposite and same. We have to retrieve it outside first and get our anchor inputs, positive inputs and negative inputs, and pass into our model, get the anchor embeddings, positive embeddings, negative embeddings, and then pass it through our loss function. Because recall, the triplet margin loss expects the anchor, positive and negative. Then we can just simply do a back propagation and just run it. So once you do that, you just run it and you start fine-tuning it. So this will take about roughly about 15 to 20 minutes, I'm not too sure. Okay, so it took about 20 minutes to finish, and let's actually get back. So now we can actually tune our, get actually our embeddings after we tune and see how the model actually managed to learn. So we're just going to refer back to our get BERT CLS embeddings. And we notice that this has the last hidden state, so we don't really want to use that because our contrastive BERT already outputs the last hidden state. So we just need to go ahead and remove that part. So let's just call this another train, something like that. And we don't need this part. So that's the only difference. Obviously, you can just combine these two functions with train flag or something like that to make it much nicer. Okay. So yeah. Okay, so once we're done with that, we can go ahead and get our train embeddings itself and the test BERT embeddings itself. Okay, so now we're just gonna get the test CLS after and train CLS after, just pretty much the same code as earlier. And just call the different few functions. It just take a couple of minutes to finish. Now we're just gonna get and generate our t-SNE graph as we did earlier. So let's go ahead and get our sample indices. Pretty much the same code. You can just copy earlier, just and adjust the test CLS before to test CLS after. And we're just gonna get a test t-SNE to the embeddings right after. State 42, perplexity 30, and iteration 300 fit transform on test it after. And yep, let's go ahead and run that. Okay, and then we can go ahead and just plot our embeddings and use the same code that's done earlier. Okay, and let's see how it does. Well, as you can see, wow, it actually does a nice separation now. So now there's a purple cluster here and there's an orange cluster here. Yes, there's a couple of mismatches here, but it's way better than the earlier one that's here. There's a lot of purple oranges all mixed together. So now there's at least some sort of learning that's going on here. So that's a very good start for us. Know that the embedding is actually learning some hard separation between sarcastic and non-sarcastic. Now for the actual $1 million question, how does it actually perform? So let me just go ahead and separate this out. Fine tuning. Make it a nicer notebook. And actually now let's actually train a logistic regression model and see how the performance actually improves. So see if I actually imported this. No, I didn't. Okay, so let's go ahead and import the logistic regression and the relevant metrics that we can actually use. Okay, so let's go ahead and run a logistic regression before, and we're going to run it after. So let's go ahead and fit on my train CLS before, and once we do this, we can go ahead and predict on our test CLS and then get our actual classification score. So let's see y predicted before, then print classification report, and y test and y predict before, and let's go ahead and train it, see how well done. And while we're waiting for that, that's already done. So it's up against 0.86, which is quite good actually. So it is more than 0.85, nearly 0.9, and not surprising because it's using BERT embeddings, which is way more powerful than most static embeddings like waterwag or glove. So, but now we're actually going to see how well a fine tuning actually works. And so let's regression after, train it on our train CLS after. This is the embeddings that we get after it. And then test CLS after, and after as well. Okay, just make sure double check. Okay, seems alright. Let's see how well it does this time. Oh, amazing! So it's like from 0.86 to 0.92, which is pretty amazing, like a 6% increase. So as you can see, that's the power of fine tuning, and this is only using random sampling. There's way more powerful loss functions, sampling techniques that we can use, but this is just a starting point to help us understand how contrastive learning actually works. And the code is provided for you all to actually go ahead and explore and see how else you all can develop on it. So yep, thanks for watching.